In this video, we're going to cover the networking fundamentals you actually need for system design interviews. Every system you design is built on a foundation of networking. Ultimately, networking boils down to one thing: allowing independent devices to communicate. We're going to talk about the software abstractions that dictate latency, throughput, and reliability. At a physical level, networking is just data being sent over a wire or the air as voltage changes representing ones and zeros. But as humans, we can't reason about voltage. So we built layers on top of this, known as the OSI model, to give us abstractions we can work with. While the OSI model has 7 layers, in a system design interview, we really only care about 3. Layer 3, the networking layer. This is where IP lives. It handles routing packets from machine A to machine B. Layer 4, the transport layer. This is TCP and UDP. This handles reliability, ordering, and flow control. Layer 7, the application layer. This is where your code lives. HTTP, WebSockets, gRPC, the protocols your applications actually speak. Let's break down the life of a request to see how these layers stack up. To understand latency, let's trace a simple request, a client trying to load google.com. Step 1, DNS resolution. The client can't route to a name like google.com. It needs an IP address. It queries a DNS server to resolve the domain. This introduces our first latency penalty, the DNS lookup time. Step 2, TCP handshake, layer 4. Now the client knows the IP, it initiates a connection using the TCP three-way handshake. First you have the SYN, client says I want to connect, then SYN ACK, server says I hear you, let's connect, then the ACK, client says connection established. The latency impact this takes 1 full round trip time, or RTT. Step 3, TLS handshake, also known as the missing step. A crucial detail here in modern web development is we almost never use plain HTTP, we use HTTPS. This means after TCP is established, we need a TLS handshake to negotiate encryption keys. Depending on the TLS version, 1.2 or 1.3, this adds 1 or 2 additional round trips before we can send a single byte of application data. An interview tip, don't forget this. The overhead of establishing a secure connection is significant. Step 4, HTTP request, layer 7. Finally, the secure tunnel is open. The client sends a HTTP GET request. Step 5, the response. The server processes the request and sends back the HTML. Step 6, the teardown. When the session is done, the connection is closed via the TCP 4-way handshake. You have the FIN, the ACK, the FIN, and the ACK. Let's zoom in on the lower layers. Layer 3, the Internet Protocol. The network layer is dominated by IP. Its job is routing and addressing. Devices get IP addresses automatically through DHCP, Dynamic Host Configuration Protocol. It works at both levels. Your home router runs DHCP to assign private IPs to your devices, and your ISP runs DHCP to assign your router its public IP. Private IPs like the 192.168xx range are used inside local networks. They're not globally unique. Thousands of networks reuse the same address. Public IPs are globally unique and routable on the open internet. They're a finite resource managed by RIRs, Regional Internet Registries, 5 organizations that allocate IP blocks to a region of the world. NAT, or Network Address Translation, bridges the two. It lets all your private devices share a single public IP. In system design, you rarely design IP itself, but you must assume it provides the connectivity. Layer 4, transport, TCP versus UDP. This is a common trade-off discussion in interviews. TCP, or the Transmission Control Protocol, this is the internet's workhorse. It is connection-oriented and stateful. It's got reliability, it guarantees packets arrived. If one is dropped, it resends it. Ordering, it guarantees packets are reassembled in the correct order. Flow and congestion control. It prevents the sender from overwhelming the receiver or the network. Default assumption. Use TCP unless you have a specific reason not to. UDP, User Datagram Protocol. UDP is connectionless. You throw packets at the destination and you hope they land. No guarantees, no retries, no ordering, no handshake. Why use it? Speed. In real-time applications like video streaming, VoIP, or gaming, waiting for a lost packet to be retransmitted causes buffering or lag. It's better to just skip the lost frame and show the next one. The modern twist, Quick, which powers HTTP 3, is actually built on top of UDP. It adds TCP-like reliability, retries, ordering, but in the user space, avoiding TCP's legacy bottlenecks. The biggest one, known as head-of-line blocking. HTTP 2 multiplexes many streams over a single TCP connection, but TCP doesn't know about those streams, it just sees one ordered byte stream. So if one packet is lost, TCP stalls everything while it waits for the retransmit, even packets for completely unrelated requests. Quick fixes this by making the transport layer itself stream aware. Streams still share one connection, but ordering and retransmission are handled per stream. Lose a packet on stream A, only stream A waits, stream B and C keep flowing. Layer 7, Application Protocols. This is where you make 90% of your system design decisions. HTTP and REST. HTTP is the foundation. It is a stateless request response protocol. Stateless is the key word for scaling. It means no server needs to remember previous requests, so any backend server can handle any request from any user. REST, or representational state transfer, is the standard design for HTTP APIs. Resources, you think in nouns, users, orders, not verbs like update user. Methods, get, read, post, create, put or patch, update, and delete. Interview verdict. Make REST your default. It is universally understood, easy to debug, and easy to cache. GraphQL. REST has a problem. Overfetching. Getting a huge JSON blob when you only needed the user's name, and underfetching, needing to make 3 calls to get a user, their posts, and their comments. GraphQL solves this by letting the client ask for exactly what it needs in a single query. The trade-off, it adds complexity to the back end. Caching is much harder with GraphQL than it is with REST. Interview verdict. Use it when the front-end requirements are complex or rapidly changing, such as a mobile app with many different views. gRPC is Google's high-performing RPC framework. It uses protocol buffers instead of JSON. It uses binary serialization. Protocol buffers. Instead of JSON, which is text, it uses binary serialization. It's smaller and faster to parse. It's strongly typed. You define a .proto contract. Interview verdict. This is the gold standard for internal microservice communication. If service A talks to service B inside your data center, use gRPC. For public APIs, stick to REST and JSON because it's easier for third-party developers to consume. Server-side events, SSE. Sometimes you need the server to push updates to the client. For example, a live auction, a stock ticker, or order ships notification. SSE opens a long-lived HTTP connection where the server can push text data. The pros are it's simpler than WebSockets, it uses standard HTTP, so it works well with standard load balancers. Reconnection is handled automatically by the browser API. Cons. It's only one way, server to client. If you need bidirectional communication, you'll need WebSockets. SSE connections can also time out, requiring the client to reconnect, though the browser's event source API handles this automatically. And because SSE runs over standard HTTP, network intermediaries can buffer messages, so they may arrive in bursts rather than streaming smoothly. WebSockets. WebSockets provide a full bidirectional persistent connection. After an initial handshake, the client and server can send messages back and forth freely. The use cases: chat apps, multiplayer games, collaborative editing like Google Docs. The hidden costs. WebSockets are stateful. The The server must hold an open connection for every active user. If you've got 100k users, you need 100k open file descriptors and memory buffers. Load balancing becomes harder because you can't just round robin individual messages. WebRTC is for peer-to-peer data. It allows a browser to connect directly to other browsers, skipping your server entirely for the data transfer. Though if a direct connection fails, a turn relay server acts as a fallback. The use case here, audio and video calling, Zoom, Google Meet. The complexity it adds requires a complex setup with stun and turn servers to punch through firewalls, but it gives the lowest possible latency. So here's the full picture. Everything we've covered sits in 3 layers. Layer 3 IP handles addressing and routing. Layer 4 TCP or UDP handles how data gets delivered. And Layer 7, the application layer, is your toolkit. This is where you make your design choices: REST, GraphQL, gRPC, WebSockets, SSE, WebRTC. Each one is a different tool for a different job. And they all sit on top of the same foundation. Let's recap with the decision framework for your interviews. The default: start with REST over HTTP. It handles 90% of use cases. It's stateless, scalable, and simple. Internal services: if you have high throughput microservices talking to each other, switch to gRPC to save bandwidth and CPU. Otherwise, stick with REST. Real-time, low frequency: if you need stock ticks or notifications, use SSE. Do not over-engineer. Real-time, bidirectional: if you're building a chat app or game, use WebSockets. Be prepared to discuss the stateful scaling challenges. Video and gaming: if you need raw speed and can tolerate the data loss, drop down to UDP or WebRTC for P2P video. Complex front end: if your API is serving many different mobile and web clients with different data needs, consider GraphQL. A few pitfalls to avoid: don't over-engineer. If your use case is basic CRUD, REST is the right answer, not WebSockets. Be aware of latency costs. A single request involves DNS lookup, TCP handshake, and TLS handshake. That's around 200 milliseconds, and at a scale, these can add up. And always show awareness of trade-offs. UDP gives you speed but costs reliability. GraphQL gives you flexibility but costs back-end complexity. The final tip: system design is about trade-offs. Don't just pick WebSockets because they sound cool. Pick them because you identified a specific requirement for low latency, bidirectional communication that REST couldn't solve. The justification is what gets you hired.